Okay, so welcome. Thank you all for joining this webinar about electronics product development. So my name is Clemens Valens, Clemens Valens, if you prefer. I'm a technical manager at Elektor, and I'm the moderator of this webinar. Well, these are the subjects that we are going to treat in this webinar. We will talk a little bit about Moore's law and the future of it, the process of developing products, using also, of course, modern prototyping technologies like fast prototyping or rapid prototyping and 3D printing and things like that. We will talk also a bit about the impact of COVID-19 on electronics product design, and even about a product designed for or against, I should say, COVID-19. Maybe we also talk about some best product design practices. And we do all this with three guests in a random order. Well, it's not totally random. It's actually in alphabetical first name order. So we start with Jason Long. Jason is based in Canada, Calgary, Canada, what we all remember, of course, from the Olympic Winter Games from a long time ago. Jason is a seasoned embedded electronics engineer, and he runs his own company, Enginuix, and he's also very active in education. My second guest is Ruben Vleuten, who is a co-founder and technical director of FROLIC Studio in Amsterdam, in the Netherlands. Ruben is an industrial designer with a lot of experience in product design. And our third guest is, once again, it has become a habit, Stuart, engineer and journalist from Munich, Germany, from where he produces content for Elektor. Before we continue, we have a giveaway. We will give away one of these kits. Yeah, one of these kits to one of the participants in this bundle. It's a bundle actually. This bundle contains this board, a development board. This is designed by Jason himself, and it's accompanied by this book, which was written by Jason, and we put it in this box. We also have three of these books for three participants. Okay, so we will announce the winners of this giveaway at the end of the webinar. They will be randomly chosen from the participants, so you have to stay until the end, if you want to win one of these prizes. As an introduction, yesterday my Wi-Fi module of my laptop died. This is it. And so I opened my laptop to extract it. And looking in my laptop, actually, there's nothing inside really. There is just a PCB with some parts on it. It's a big heatsink, which takes about the whole surface of the laptop. And the heatsink is stuck on a module, and that's about it. And this shows that if you compare it to a main board of a PC from the, 10 or 20 years back, that Moore's law has been working for many years now. It really enabled, well, it's not the law that enabled it, but it's empirical law, of course. We can see that from a big board with big chips, we went to very small modules with chips inside that can do much more than what they did 20 years ago. However, we cannot continue forever with Moore's law, and that's what Stuart wrote an article about. He looked into Moore's law and its future. Stuart, can you tell us a bit more about it?
Yeah, so Moore's law has been around for a very long time, and it's bandied about, especially in the financial press, when big semiconductor vendors are talking about technology improvements and what we call a process node. So process nodes are, in essence, the definition of how small all of the items on a chip can be, how thin all the connections can be on a chip. And the reason this is big news is because the smaller those little wires and those transistors are, the more transistors you can get onto a chip, and typically they can also be faster, and you can get a lot more functionality on the same surface area. So Moore's law and the idea of getting more and more into one single chip has been a driving force. of the semiconductor industry. And the reason for writing this article was that Intel announced that their 7 nanometer process is actually now 12 months behind their planned schedule. So this highlights again how challenging it is to keep on making everything thinner and smaller all the time. Now, Moore's law came about due to a gentleman who went by the name of Gordon Moore. He was a co-founder of Intel, so it's appropriate that this sort of news is linked to Intel. And as you said, it's an empirical relationship. And his statement in the 1960s, 65, was that he expected the number of transistors per square millimeter of chip to double every year. But by 1975, he'd tuned that back a little bit and said it's going to be a doubling of transistors per square millimeter every 2 years. So although his statement was more sort of a prediction about the growth rate or the growth rate of transistors on a die, it's actually ended up being more of a goal by the semiconductor industry to really pack as much into one chip as possible. Now, for vendors like Intel and AMD, who are obviously well known for their fast and powerful processors, but also for graphics card manufacturer Nvidia, and also DRAM manufacturers like Samsung, Micron, and SK Hynix, this sort of pursuit of the bleeding edge of miniaturization has been the thing that have kept them at the forefront of their business markets. And but it is not the be-all and end-all, as we know. There's lots and lots of other semiconductor vendors on the market, and they're not all trying to be as small as absolutely possible. So what I wanted to do was take a look and find out what some of the alternatives were. One of the key things, though, to look at first is actually Gordon Moore's original paper, because as well as making this prediction about the future of the number of transistors per die, he also made his what they've called the Day of Reckoning passage. And in that, he made it clear that, and I quote, "Under certain circumstances, we should consider whether we really want to build these component-crammed equipment. It may prove more economical to build large systems out of smaller functions which are separately packaged and interconnected." Now, the significance is this is quite huge, and we're actually seeing changes coming about because of that. One of the things that was clear was that analog components were never going to scale as well as transistors. If you need a capacitor, the capacitance of the capacitor is dependent on the area of the overlap of the plates. So if you need a capacitor of a certain size to implement, for example, the memory of a DRAM, and it's so many femtofarads or smaller, it's going to have to be a certain size, and no amount of process improvement and making it miniaturization is going to make that capacitor any smaller in a planar structure. Yeah, so when it's laid out flat in a 2D structure. So lots of things have happened over the years to try and provide innovation in different ways, and that was the focus of this article. Now, one of the things, areas where is actually coming to fruition with this passage, this Day of Reckoning passage, is actually back at Intel again, who have the FPGA technology Stratix 10. Those devices are actually made up of what they call chiplets. And the idea behind chiplets is that instead of trying to get everything onto a single die and then package that up, what happens is that you make many individual die and you put them all onto a substrate next to one another. And therefore, you have the advantage that if you've got particular functionality, let's say a serializer, deserializer, which is an analog type of interface, you can choose a manufacturing process which is more appropriate for that analog functionality. And if you need to then connect it to an FPGA, the FPGA can be built in a process node which is appropriate for that digital functionality. And then those two die can be put next to each other on a substrate. And obviously, having more than one die in a package is nothing new. We've had sort of stacked die and multiple die packages. But the difference here is actually the way that and the technology used to actually interconnect all of those chips. They have something called an embedded multi-die interconnect bridge, or EMIB, and this is a specially designed piece of electronics which allows these different chiplets to be connected to one another. One of the advantages of this approach is that those chips can then also be placed very close to the appropriate balls of the package, so that you don't have EMC problems and layout problems later on. And furthermore, the yield for a smaller die is much better than a yield for a larger die, which means that if if you're having problems creating the analog element, or the analog element of a chip is the bit that fails, if you regularly during manufacture, if you separate that out into a separate die, obviously throwing those away doesn't impact the rest of the chip, which is fully functional and digital. So there's lots of advantage to this chiplet approach. And that's what we actually see here on the next slide, on the top right, these substrates with various different chiplets all placed around them. The other thing that's going on in the industry, and most people probably have heard of at some point, is the idea of moving upwards. So instead of having a planar 2D approach to chips, we now have lots of technologies which actually go upwards into the third dimension. And this is the case with products such as flash memory from, one example highlighted here is from Kioxia, which was formerly Toshiba's flash memory division, and their 3D BICS technology, which is bit column stacked NAND memory. What they've done is actually they've essentially, you can imagine that these planar designs, which were in 2 dimensions, they've actually taken those and folded them up into 3D structures. And if you could look at them underneath a microscope, they'd actually look like little housing, little blocks of flats all sticking up out of the ground. And by moving to that third dimension, they've actually been able to move away from this need to keep making the transistors smaller. Now the transistors can be made a bit bigger because they've got space to grow upwards. And as a result of that, the quality of the memory cells that they're implementing can actually improve. They can actually now have more electrons per transistor than they did with the old planar approach before. And more electrons per cell means you've got more reliability and also less wear over lifetime. So the latest 5th generation of those 3D technology is now 112 layers high. And that has actually made it possible to create a single die with 1 terabit, that's 128 gigabytes of memory on a single die. And when you think again that those are then stacked on top of one another inside a package, you actually get enormous amounts of memory on a single chip, which is ideal for the future of automotive, with autonomous vehicles, and also with smartphones needing ever more memory. So another aspect of that as well, another innovation within that technology as well, is something called through silicon vias. Now, when the die, because the flash die is always the same size, those flash die can actually be stacked on top of one another. And rather than bond them with wire bonds, which is how we're used to the chip being connected to the wireframe of the package, through silicon vias actually allow the silicon chips to be connected through one another. So in the same way as you have a through-hole via on a printed circuit board, and they're all stacked up on top of one another. Because of the short distance then between each die, it actually reduces a lot of the EMC problems, and this allows the flash memory to actually operate at a much higher data transfer rate. And this is really important when we're trying to implement new types of interface technologies, such as PCIe, NVMe, and UFS on flash memories. Another way of innovating within the flash memory area has actually also been to increase the number of bits that are stored in each cell. So typically when you think of the data stored in a microcontroller, every cell of memory in flash stores 1 bit of data. That allows you, you can actually then improve on that by taking an approach which is called the multiple level cell, or MLC approach. And with that, instead of having a high voltage and a low voltage in each cell, you actually store one of 4 voltages, and each voltage is then indicative of a 2-bit value. So now I can actually store 4 values per cell. We can then take that concept further, and we can, instead of having just 4 voltages, we can now store 8 voltages per cell, and each voltage represents then 3 bits, and that's a triple level cell approach. So by taking that approach, we can actually increase massively the amount of storage in the same piece of silicon, but that does come at the cost of a higher wear. So when we store charge in flash memory and then we erase the flash memory again, it actually physically wears out the flash cells and over time, eventually they will fail. So you can't actually store data on them reliably anymore. And using these multi-level or triple cell approaches actually is harder wearing. But that problem is resolved with the Kioxia memory technology due to a different way of storing the data inside the memory. So we're also very used to the use of silicon in the semiconductor industry. That's what we're known for. But in recent years, there's been a lot of work being undertaken to look at alternative types of materials with which MOSFETs and transistors can be built. And that research has driven us towards a range of technologies which are collectively known as wide band gap. And that's because they basically have a much higher band gap of 2 to 4 electron volts versus 1 to 1.5 electron volts of silicon transistors and MOSFETs. Out of that technology research, 2 key sort of runners have come into being. That's silicon carbide, or SiC, and gallium nitride, which is also known as GaN. Now, GaN transistors provide an edge over silicon transistors in that they have a much lower RDS on, so their on resistance is very, very low, and they can also operate at much higher frequencies. And if they're used in, for example, digital power supplies, what that means is that we can now get really, really efficient power supply implementations because they have almost lossless switching due to their zero reverse recovery properties. So that means, for example, that if you have a silicon digital power supply today, which maybe reaches 97.5%, almost 98% efficiency, with GaN, it's possible to move that to 99% or maybe even better. And obviously on an individual scale, that's maybe not so amazing, but when you think about a server farm for Google or for Microsoft or Amazon, and all of the power supplies that are being used to power all the computers in those environments to store all our data, that total cost of ownership actually is significantly impacted by the reduction of electricity that's used. Silicon carbide MOSFETs, they're also faster than MOSFETs, but one of the nice things about them is they're much more robust than MOSFETs, and they have a much higher power density at that higher voltage of operation. And in that respect, that makes them slightly better in certain circumstances than GaN transistors. They're also much easier to use than GaN transistors. SiC MOSFETs can be driven by the same gate drivers that have been used in silicon designs. The only recommendation is that the gate voltage needs to be ever so slightly higher, about 18 volts compared to 15 volts of a silicon MOSFET. They're very, very robust. They can be used in hard switching applications such as continuous conduction mode, totem pole power factor correction designs. And again, trying to make a power factor correction converter in a digital power supply can result in a 99% efficient solution, which is an excellent starting point before you then start working on the DC-DC converter behind it for the rest of the power conversion design. Of course, innovation happens also in other ways, and you can see the historical improvement that happens over time if you look at certain products. Obviously, DC motors are a core capability or functionality of many different applications. They're used all over the place. There's loads of them built into automobiles, for example, as part of the air conditioning and ventilation system to control all the vent flaps. So they're still used in significant numbers, even though brushless DC motors in many cases are more efficient. And for them, a long time ago, the H-bridge circuit was developed in order to provide a very compact and efficient way of controlling the motor and also controlling its direction. The Japanese at the time were obviously very keen to have that integrated into a single chip device, and the TA7291 highlighted here was actually built into lots of video recording machines to support the insertion and ejection of video cassettes. I hope there's enough people out there that still remember what a video recorder is and a cassette. So that particular design, for example, that was a bipolar design, got the 4 transistors there, and it had a very simple regulator and protection circuitry that protected against overheating and overcurrent. That same design has more or less been updated by the design we see on the right-hand side, which is called the TB67H450. This device has been moved to what's called a bi-CD process. So that's a combination of bipolar, CMOS, and DMOS technologies. And as a result of doing that, we can now use 4 MOSFETs for the H-bridge, and the on resistance of each of the switches has fallen from 4.75 ohms in the old design to just 0.6 ohms in the new design. So just small things like that actually make a massive difference in terms of efficiency. That also reduces the amount of heat that the device generates when it's in operation. And another aspect of it is, of course, it's on a new technology. It's a smaller die, and that actually falls into a smaller package, as we see here. On the left-hand side as well, we see those older packages, even though there was a surface mount option available at the time, which is 30 or 40 years ago. The heat sink, the heat sinking is implemented through these wings, metal wings that come out of the side of the device. With a new device, heat dissipation is much less from the beginning, and sort of a further innovation is in the packaging here, because there's a heat slug in the bottom of that packaging, and that allows the heat to be dissipated directly from the die and into the printed circuit board, which is probably more than enough heat sinking and heat dissipation for this type of application straight into the circuit board, and negates the need then for more complex heat sinking implementation. So that new device as well, instead of just driving motors of up to 2 amps, it can support motors of up to 3 amps current draw. And instead of operating at just up to 20 volts, it now can support 50 volts. So innovation comes in many different forms. And while sort of teraflops and zettabytes make for great headlines in the financial press, and we're all keen to see what the next generation of Intel processors is going to look like, and how fast the next NVIDIA graphics cards are going to be, that's not where all of the innovation occurs. Innovation is occurring all the time in terms of the packaging, in terms of how we connect die to one another. It's happening around looking at alternative ways of manufacturing in silicon by going up. It's looking at different types of substrates. And it's also, as we see here, just taking old designs and updating them for new applications.
Okay, thank you, Stuart. I really like the idea of upgrading, reusing old designs. There are quite some examples of good chips actually that disappeared because of the manufacturing technology improved, and they didn't bother to update or redesign the chip for the new technology. They just obsoleted it. But that's a shame, because there were a lot of good ideas in there, and so this is a good way to get them back, right?
Yeah.
I was also wondering, you see it also in software when you have a lot of components on a large or on a small surface, but the problem is to interconnect everything. Do you know anything about the interconnection technologies they use, or?
Sorry, in software or in hardware?
No, in hardware. When you make an FPGA, for instance, it's quite a difficulty to distribute the clock, for instance, all over the chip. So.
Yeah, I've not had so much experience in sort of FPGA design. I think the development tools are just huge. It's hugely complicated. When you look at the Stratix family, for example, you download them. It's just you wonder where to start as a beginner. That's for sure.
Well, let's move on to our next guest, which is Jason. Jason is, as I said, is very focused. You are very focused on education, and you even designed your own university program, Embedded in Embedded. Why did you do that?
You know what? It goes back to when I was still an engineering student, and like I might say many engineering students are, I was very shy. I had a lot of trouble speaking in front of people. So that was a problem I needed to solve. And at the same time, I had learned about microcontrollers, and this was like a PIC 16 series. This is in 1999, I believe. So I wanted to learn more. I was never really good at sticking to extracurricular projects without some sort of accountability. So the idea of learning and sharing that with my peers just kind of solved all my problems. So yeah, it grew from there as a student, but as I entered into the embedded systems industry, I just decided to keep on sharing what I was learning. And it became, of course, a lot easier once I actually knew what was going on. And, decades go by, right? And that program became more and more popular and important in the community. And I looked at sharing it across Canada in different universities. And then eventually somehow wound up in China doing this. Like it's amazing how these things progress, and just because you're passionate about something, and that's always what has like ultimately driven me. It's the most consistent part of my career, and it has really nothing to do with earning money or what I'm supposed to be doing from 9 till 5.
But besides doing education, you also design products with your company, Nginx. Can you tell us something about that?
Yeah, that's throughout my career. And this slide actually is all these things are things that I was involved in the design. Not so much the light armored vehicle. That was from a time that I worked at General Dynamics Canada, but I was still leading a team that was in the product development and test. So if we kind of fast forward to right now, where Nginx is, the products that I've designed there are really for the makerspace and for different developers doing embedded. Most of those came out of frustration from my own development that, there's different, little tools that you need to help you on a day-to-day basis, but then also just exploring different technologies and how do you do that without actually making it and using it. So as I was making a lot of these things, I just had on breadboards or very temporary circuits, and then kept on using them, and they became very useful. And so I started to productize those. But they're very developer oriented, which I think is quite a distinction between the products that I've developed as a design engineer working for other companies. And that's a few of those from various companies are on that slide as well. So I got into gas detectors initially, which is like safety equipment that you wear for when you're in mines or processing facilities and things like that. So they're basically the yellow canary that beeps when you're going to die and gets you out of there. Which it was my first job, and it was not what I remember reading that job description. I said, I don't want to work in dirty oil and gas. But it was really interesting because I learned right away that regardless of the industry, the guts inside these electronics is essentially the same. It doesn't matter if you're making medical devices or industrial devices or consumer electronics, a microcontroller is a microcontroller. So I did it's called BW Technologies. They eventually got bought by Honeywell. Did that for a little while, and then I went over to a company called Blackline Safety, and we were doing GPS products. So that was great to start getting into tracking devices and things like that. We built that thing on the white and blue case at the bottom is actually a kidney transplant device. I learned that kidneys, if you donate a kidney, it often ends up literally in a paper bag in a taxi, and they get lost. They get left on loading docks and things like this. Seems crazy, but we had a company out of the US approach us and say, we need to track our kidneys. Can you do this? We said, absolutely, we can do that. So we did it. And this, in doing these products, you really see how complex building products is. So yeah, we can put microcontrollers together, build circuit boards, program them, and one or two people can do that for a relatively simple product. But then you look into the industrial design and the actual production. Some of those gas detectors that I did, they sell about 500,000 of them per year, which compared to an iPhone is not that much, but still, even I remember to this day, it was about my third year of working, and we did the first run of 5,000 pieces of this gas detector. And we had production on site, and I went back there, and 5,000 of any device, they're about this big, and just they're everywhere. It's like they invaded. And the trick with those is that we happened to be stuck with a one-time programmable processor, which meant if it wasn't right, it was garbage. And it was terrifying that, like, I hope this works, and it did, thanks. But it's just amazing how things scale. And then, you know, throughout my career, even to this day, I've learned, you know, the intricacies of supporting that, you know, what supply chain is, but even down into marketing and sales. And it's just such a huge ecosystem involved in making products that there's so many people involved. So I talk a lot about building relationships and things like that. I speak more about building personal relationships these days than building technologies. Overall, it's amazing. It's incredible to be able to build something tangible, and it's more incredible to be able to work with all of the people and see everything coming together to make that thing go.
Can you say something about how you design a product?
Certainly. This is that's where this side kind of fits in. I wanted to, at least from just my perspective and, you know, what my duties are when it comes to product design. In the past, now that I do a bit more, there's, you know, I'm involved in some other stuff, but I think at the very beginning, if someone, you know, people in this webinar and in your community, they think, well, what do I need to actually do to get, you know, maybe a proof of concept or something? Sorry, missing gloves. And that's distracting. You'll figure it out, guys. So a lot of times when you've got an idea, and that of course is where everything starts, from an embedded design perspective, and even, you know, just from a maker perspective, you're trying to get that into something that's real. And I think if you're going to be serious about doing product development, you have to think big enough that, you know, you're not just going to breadboard something together and take that to, you know, to pitch that into you know, investors or someone that's interested in this. You have to go a little bit further. And that's where it can get very difficult. So you might be thinking, you know, if you're going to really do something, you're probably going to be producing 100 or something, or, you know, of this sort of device, because you need to test it. You need to give samples. Everybody always wants samples of these sort of things. So that already becomes a little bit more complicated. So I want to take you through a little bit about how I would make something. So again, it starts at an idea, and then there's sort of, as we go through the boxes on the slides here, so you got this idea, and then you need to make something. So that, to me, from my perspective, is a combination of firmware design and programming. There's going to be some sort of circuit design in there and creation of that. And I think there has to be some sort of, I say this carefully, industrial design. I'm not an industrial designer. Industrial designers are brilliant people and can make or break your product. I finally did buy myself a 3D printer a couple of years ago, and I've been tinkering around with SolidWorks. It's a lot harder than it looks, but at least I can make boxes now, which is actually significant. It's very interesting. If you take a circuit board to someone, let's call it a layman person, and you're like, oh, it does all this. All they kind of want to think about is that this looks like a circuit board and it's not a product. But you can even just take a cheap plastic box and put it in that box, and suddenly it's a product. And then you can print a label on it, and it looks so much more. So I think that's an important element. And it's, if you can also start anticipating at the very beginning about what this thing is going to be. Is this actually manufacturable? How am I going to manufacture it? All these sort of things. The more you know, the better prepared you are to look toward the future. And I think that is the essence of experience, right? If you've never designed a product, you have no idea what you're going to run into. Having designed many products, I already know at the end all the different hurdles that I'm going to jump through. Okay. So you get something working, you've got a circuit board in there. The question is then, how do you put parts on? Where do these components come from? Where do you source them? We talked about as I prepared these slides, we talked about, just with Clemens, about, do I want to actually show some specific companies on here? And we decided that, yeah, I do. I want to actually show you guys some of the companies that I use, because, not that I'm in any way connected with them to make money or anything like that, but it's so hard. There's so many. If you look up, how do I make a PCB, you will get 10,000 different manufacturers of a PCB. So how do you choose one? So you've got this design. The first thing is, I need a board. There's a US company called Oshpark that has kind of emerged as a really good way to do fast prototype circuit boards, and they're very high quality. They ship worldwide for free if you use regular post, and it's like $5 a square inch, which is really, really low cost comparative to something else you get. But you can't, you're limited. Of course, there's some limitations in there, and you're not going to take one of those PCBs and stick it in a surface mount machine to populate a whole circuit board. So you're looking at a whole few orders of magnitude higher in cost to go to that level. And so you get a panel of circuits. I should have brought one here. A panel of circuit boards that has to be mounted and put through a machine so that all the parts are picked in place out of reels and things like that. And that's how you build high quality circuit boards. You're not going to hand solder 100 prototypes successfully, and it looks like crap, right? You can't take this. If you do that, if you show someone a hand soldered circuit board, even though it is functionally correct, you're just not going to be taken seriously. I think you need to have that quality manufacturer. So Enigma Interconnect is a company that I've used since my first career started for 20 years. So they're reliable to me. I know they're there. They're in Canada. We can save offshore discussion for another webinar, but you're not going to go offshore for building prototypes. Let's just say that. Where do components come from? Here in North America, DigiKey is really, really popular, I guess. A little bit expensive, but so easy. So you can source your parts from there. You can get small strips of them, or you can get full reels of these parts, right? So you can actually do production level sourcing from the same place that you're doing your prototype level sourcing. There's a cost penalty for that, I guess, via DigiKey, but they're also getting better to support things. But there's other big distributors, so like Aero Electronics, Avnet Electronics, they're worldwide. And when you're in production, when you're doing 500,000 devices, you're looking at, your supply chain is immensely important. Single source parts are like the taboo, right? You want to make sure that you can get parts from whole bunch of different vendors. For parts that are tricky, you might have to order a year ahead, right? There's supply chain, especially in COVID times, we tie things into there. There was some huge issues with a lot of different components that were being sourced out of China factories that were closed. So some of that first company that I worked for, we would sometimes warehouse 2 years of parts. So, you're looking at tens of thousands, if not hundreds of thousands of dollars for just a few components to sit on the shelf to make sure you've got them so that you can keep your production line going. Because one part, if it's missing, you're shut down. So, and then the last thing about to sort of keep in line with the industrial design and the physical device part of things, 3D printing is definitely helpful. You can do a lot with a desktop 3D printer. But then the next level, where do you go to? And just recently, actually, on one of the contract designs that I'm working with, we had to go to some high-end 3D printing, and they're very expensive, but the customer wanted that. They wanted very true-to-life prototypes, but they didn't want to spend $70,000 on tooling the actual device that we don't know if it's going to work or not. So we spent a few $1,000s to do some high quality 3D prints. So all of those things, you've got your design, you've got these basic parts, and then you got to put them together. So the two companies that I've highlighted here, Protogir is just a new company that's popped up in my own city. It's run by one of my former students in Embedded, and this is what I love about my network and how it grows. And I think I saw Richard talk about Kevin in the comments there. So he's a really strange person who has identified that there's this niche for small run surface mount population, and it's beautiful because a lot of companies won't talk to you. If you say, I want to do 20 boards or 50 boards, they'll say, great, have fun. We don't want to deal with that because it's just not worth it. But Kevin is trying to develop a system that he can do that. So you have to have some sort of option or else pay a lot of money. So there's another company out of Vancouver called Dorigo. They have full SMT lines. There's a couple in Calgary as well. But you're looking at, $5,000 to $10,000 just for the process, right? So versus a small turn like Protogir, he'll charge you maybe a few $1,000s, but it's still thousands of dollars, right? And it all kind of depends on where you're trying to go with this. But overall, I think it's important just to consider how much is involved just to get that first. This is my mouse, but this is an example of something that would take a lot of money to get even into the process or into a prototype phase. But if you're going to be serious about product development, I think you have to be prepared to do that. So know what's kind of involved from a design perspective, stuff that you can't handle or that you need some help with, and then where are these resources that are going to bring everything together and actually make that thing, turn that thing into something that is real and someone's going to actually look at seriously and have the ability to actually scale up and become a product over time.
Okay, thank you. My microphone is on, yes. In Europe, we have seen some companies popping up that propose cheapish, small run prototyping services, like Protogir, I think, with online, how do you call it? You set it all up online, you do it yourself more or less. They're all automated. In their factory, there are only 3 people working. It is still quite expensive, but from there you have to go to mass production at some point. Then you have to change the manufacturer. They have their own production lines, their own systems, etc. So at some point you will have to do some part over again, I think, to adapt it to the mass production.
Yeah, for sure. And a lot of the smaller companies that are popping up, I've seen, you're limited to the components that they stock. So you basically have to look at their library of parts and design your device using their parts, because they've got tons of machines set up with all of these components, so they don't have to be switching out parts and doing customizations. I think if you need customization, you're looking at a huge price increase or premium that you'd have to pay for that. So it's one of those things that sounds really great. The problem is that if you're building something unique that no one else has built, there's probably at least one part on there that is unique. And then how do you program it? How do you, there's so many things that can go wrong, I guess. But that's part of the challenge, and it's part of the fun is, maybe you get 99% of your components populated, and then you hand populate 3 parts or something like that on the final design. So you can always adjust, but you have to be very, very careful. Can you do it? Is it going to work well? And again, what happens when it does come to mass production? Are you willing to put a bunch of money into sort of a temporary solution and then totally retool into something else? Can you afford to do that? Or do you take the risk and say, okay, well, I'm going to get my proper panels, I'm going to pay for SMT programming and all that sort of stuff. There's a lot of what we call NRE, which is why can't I think of NRE? It's like the one-time, non-recurring expense. That's what it is. It's setup fees. So like to set up a circuit board panel, it's about $1,000, but you only pay that once, and then you start paying just the board cost after that. For surface mount, it's $3,000 to $5,000 for them to program that machine. But once it's done, then you don't pay that again. So you could take that risk and be ready and let that amortize over all of the production or the products that you're doing, assuming that you're going to do a lot of products and your sales and marketing team are going to work. Or you go a cheaper route, which means that you're maybe 3 to 6 months, if not more, behind actually being able to go to mass production, which also could be a deal breaker. If someone's got a great idea and you pitch that, all of a sudden they want it now, right? So when can you ship? We want 10,000 units in 6 weeks. And you say, well, it's actually going to be 6 months. And they'll say, okay, we'll go somewhere else. So it's an amazing, intricate balance. Yes, so I sort of randomly picked some images here and things that if you're actually going to bring a product to market, there are some big things to consider. And in kind of random order here, bottom right is production. So I just recently, I did there's an art and engineering exhibit in Calgary called Beakerhead, and I think it runs around the world. And so last year, I built, it was a cow, okay? This comes from my summer camps, and the kids were making these electronic things, and we decided to build this big art cow that I got an artist to do and put it on with these persistence of vision spinning electronics things that the kids were programming in the camps. So we got all their names on there. And I ended up having to make 100 of these things, and they were 3D printed enclosures, and they had to press on, and there was brushes and like for the electric motors, and because they were spinning. I just made 100 of them, and it was an absolute nightmare. I've never made 100 of anything on my own by hand, and I was almost ready to just give up the whole engineering thing just because of that. It's amazing how long it takes to build a lot of things. So how you are going to produce that is any sort of thing in quantity is really, really important, and it's expensive to do that, especially with these contractors, because they have massive teams assembled waiting for people to come and say, build me something. So you're paying all that overhead for your particular product. So production, where am I going to do it? It's a big thing. Let's go around this from the top. Certification is also massive. So in North America, we have FCC, which is the Federal Communications Corporation. So Stuart was talking about EMC and EMI and things like that, and emissions. And every piece of electronics has to actually be tested to make sure it's not too electrically noisy. That's the gist of FCC. And that can cost anywhere between $10,000 if you pass, or $100,000 if you fail a few times. And you can't sell a product without it. In Europe, you have the CE mark, which has some slightly different rules, but ultimately it's kind of the same thing. And then if you're working in specific industries, there might actually be some specific certifications that you require before you can actually sell that product legally. So you could get to the point where you're kind of ready to go, and then someone says, oh, where's your FCC mark? And you say, oh no, and then you fail and you can't sell your product, right? So that's important. People, if you look at the middle image there, people are amazing. The further you go into product development, the more people are going to be involved, and working with those people and keeping everyone happy, keeping those relationships maintained is a lot of effort. And I've seen product developers that have this great idea, have this great product, and they have to completely abandon their engineering roles and give that to someone else and work on building their company, which is a hard thing to do and something you might not expect. And you have great people. I would recommend that you never start any sort of thing without at least one other person that is helping you out and that's there. And hopefully that grows into a great team. Marketing and sales, I have yet to figure out. I cannot emphasize how important this is. The greatest idea that you have, the greatest product, if nobody knows about it, it's never going to go anywhere. And I will tell you from experience that even if your immediate network is relatively large, a few thousand people, that's not enough to sell products. people aren't just going to buy your product because they're your friend. That's how it turns out. A few people will. Maybe 1% of your network might actually buy something from you. So if your first step to success is that 90% of the people that you know are going to support you, then that's your first step down the wrong path, because it probably isn't going to work like that. And then money. Where are you going to finance this? It is, I would say, that to actually bring a product to market, you're looking at anywhere from $100,000 to $1 million. And it doesn't really matter the product. If it's a hardware type device, a software device, an app or something like that, wouldn't have that same sort of cost. But you would be surprised at how quickly the amount of money that you need ramps up for all of these different things, even just shipping. I think that FedEx has made more money from me than I've ever brought in for my product designs and things like that on my own stuff. And it's incredible. And I mean, it's a big challenge. If you have a $10 product or a $20 product, but it takes $40 to ship it, no one's going to buy that product. And that's, unfortunately, is some of the realities if you're trying to do things on your own. So all these other things, like just making a product is almost the easy part. Getting it out there and making it into scaling it up into a sustainable type product. There's so many challenges there. But a company like Elektor, if you through Elektor Labs, through writing articles, through participating in things like this, and there's always that chance that you will hit a sweet spot, find connections that make things take off. So that's always really, really important, is to keep getting out there and keep participating in the community.
So Ruben, you are also in product design, product development, so you must recognize some of what Jason talked about. But you are more in industrial design. How does all this relate to you? Can you tell us something about what you do?
Yeah. First of all, thank you for having me. And it's indeed it's great to hear Jason talk, because there's, I think, a lot of things I can relate to, and some of the things that I guess we have slightly different angles. So a couple of years ago, I founded FROLIC Studio, co-founded with Design Studio in Amsterdam. And basically what we do is we design and develop products, physical products, which most of the time contain electronics. Some of them are smart, some of them are less smart, but it's most of the times taking something from the physical world and connect it to the digital world. I just put on the slide some of the projects that we did before, which is Smartians. That's actually a self-initiated project where we took it's basically a smart actuator, and it's basically a small motor that you can put on any product you have in your home to make dumb products smart, right? It's one of, it was a studio project, and we really love this project because it really shows what we try to do as a studio. So you have basically this small motor with all these pieces you can add to, and then when you have your washing machine, you can make your washing machine smart because you can remotely control this motor, and then you can remotely press the button on your washing machine. So you can put the laundry in your washing machine when you leave the house, go to your work, and 2 hours before you leave work, you can basically trigger your washing machine.
This is a robot finger.
Exactly. It's a smart finger. And the reason why we did it is we saw this opportunity of products getting, you have IoT and products getting smarter and smarter. And we saw this this shift where people are buying, if this whole consumerism going on, where people replacing them perfectly working machines just to make them smart. And we were like, okay, there must be a way to keep these old machines but make them smart without replacing the whole machine. So this was a bit of a provocation within that world. So it was a self-initiated project. We never really built it. It was more of a proof of concept. But we do also work for clients. That's actually most of what we do. So clients come to us with a product idea or with a problem. And one of the project was WestJet, which you probably know, Jason. It's a Canadian airline, and we made this projector nightlights for them. It's really a consumer product. But we also work together with TapUp, that was a spin-off of Shell, and they basically are a B2B business where they deliver fuel to companies with big car fleets. Say you're a company, you have a big car fleet, you have 60 cars, and what happens most of the times is that all these cars drive to the fuel pump, fuel up, and go back. What TapUp does is they reverse the project. So every day at, for instance, 6 o'clock, TapUp comes to your business and fuels up all the 60 cars. So the next morning when these cars are needed in the business again, they're all fueled up. And they have the service, and we basically help them to make the whole fleet of refueling cars smart. You can imagine they have like a bunch of these cars going around. There's a lot of logistics around it, but how do you deal with that from a logistical perspective, from a user perspective? You know, like the people driving on these cars, or the people dealing with the logistics have to know where the cars are. There's a lot of fuel being cars being refueled, so they have to keep track of the fuel, where it goes for billing systems. You have people working on the cars, how they deal with it. So we looked at them together with at a system, and we tried to make that whole system smart, which is eventually a more B2B application. And then another thing we do is like we do quite some products in healthcare. I say it in healthcare context. So we work together. We made card wash, or we co-designed it. Let me say it like that. It was together with the enzyme company, and they have these enzymes which can break down biofilm on mouth guards, but you need like ultrasonic cleaning for them. So what we did is we made this proof of concept and the design for this machine that cleans mouth guards. Again, in the consumer context. So what you can basically see is that we do a lot of different kind of products and projects, but they all always have in common that there's like some piece of hardware, some electronics, some industrial design, some physicality in there.
Sorry, can I ask you a question?
Of course.
So you do the initial design, you do some prototypes, maybe a first series. Do you take into account, or do you design also for production?
Yeah, basically what we try to do is we offer end-to-end solution, meaning that we try to get involved in the projects as early as possible in the concepting phase, when clients just have a problem or just a product idea, all the way up to design for manufacturing. And most of the times that means that we are involved up to the point where we hand over design files to our clients, which then take them to their manufacturers or suppliers, and then they produce independently. We've also done projects where we actually took care of the production. But what we actually, so we do very much end-to-end, but a lot of the focus is on these initial phases where we really try to validate products and projects, products ideas. And we very much work with the sprint methodology, which is initially designed for the development of digital products. And we kind of took that realm of the idea and we converted that into a sprint process for physical products. So what we do is that we, when a client has an idea of a product, we work in these 2-week chunks where we basically take the concept, we transform it into a product idea. We build it very quickly using all kind of rapid prototyping technologies, like quickly making PCBs, 3D printing. Like it's really about like quick prototyping. We put them in front of users and then to see, okay, what actually works and what doesn't work about this concept. It's really about trust, iteration, to very early in the process actually define if a product is worth investing further in. Because one of the things that you often see, or we often see and experience, that companies or individuals have like this idea for a product. They invest a lot of time and money in developing that product according to the ideas they have and the assumptions they have and this going tremendous amount of money and time into the research, they end up with a perfectly well-working product from a technology point of view, and then you put it in front of a user, and then a user often doesn't really know what to do with it, or is maybe not waiting for the product. And we, being a product design studio, we try to move that product, pull it forward in order to see, like, okay, what if you put it in front of users? Like, do they actually use it as you think they use it or not? And if they don't use it the way you intend to use it, like, what can you change to do so? And that's, maybe can go to the next slides, because that's one of the big challenges. And you asked us actually to talk a bit about the challenges we experience as a design studio. I think we want, yeah. Because I myself, of course, I'm an industrial designer, and although for the past 10 years I've moved more and more towards the implementation of technology and electronics, I'm still a designer in the way I'm thinking. And what you can see on the slide is that in the field that we work, you need a lot of different disciplines, right? You need, like, we have industrial designers, we have UX designers, we have electronic engineers, we have user researchers. Like, there's a lot of different disciplines you need nowadays to make a product, because it's not just electronics anymore. It's not just industrial design. It's not just designing an app. Everything comes together. And one of the biggest challenges that we find is to make sure that all these different disciplines work together and having the same mindset. Because when you ask an engineer, and that's maybe more suitable for this in this concept, when you ask an engineer to design a product, one of the design electronics, one of the things that they are thinking of is, like, they, it needs to work perfectly, and like, how can I make this cost efficient, and how can I make this and that and that. So engineers tend to think already, like, really, like, into details very early in the process, which is beautiful and pretty, and that's, like, they get totally absorbed in this field. But at the same time, we try to work in these short sprints where we try to first validate if a concept is working and actually worth investing all the time in before actually spending the time. And so if we tell an engineer, like, for instance, at the beginning of a sprint, okay, next week we want to do this user test, and we only want to have this and this and this functionality working, and don't bother about these potential problems you might encounter later down the line. It sometimes creates struggles. And it's the same way the other way around. If we work with industrial designers and then we talk with them and say, okay, please keep in mind that if you design something, that there's enough space for the electronics, right? If something can look very fancy and sexy when you make a render or like a 3D print, but if the electronics that don't fit in there, or that need to fit in there, don't fit in there, you also have a problem, right? And the same when you work with digital designers, and that's what I liked, what Jason also said. It becomes way more like about personal relationships, and how do you manage that to create like this team where you have so many different disciplines, have them all point in the same direction and work together as one team. And I think that's one of the biggest challenges we face as a company. Besides the things that Jason also mentions, like where do you source your components? Where do you make sure that you have reliable suppliers? Where, like, especially now with COVID crisis, like it makes things even more challenging. Like, how do you get, when we work in these 2-week sprints for very short, like lead times, so you have also very little margin of error. So like, where do you make sure that they order a PCB and they have a 2-day lead time, that you actually have the PCB within 2 days, right? So these are all like really fun challenges to work with. And over the course of the time, we work, like in the beginning, we work with these sprints, and later down the process, we work with more longer cycles. So first sprints are to really identify what you want to make, and then you get into these longer processes of real product development, where you then try to make things very cost efficient. Make it in a way that you can design or that you can produce 1,000, but also 10,000. Like these are longer processes. And what we try to do in the beginning is to make sure that that long process is actually worth investing in.
Very important indeed. You also did a sprint at the beginning. I move on to the next slide in a COVID-19 design.
Yeah. No, exactly. Yeah. This may be a nice example to talk about how things can actually develop. And this is a project we did early this year. I think it was April or May. And we sat together with our team, and we were talking about like COVID-19, as I guess everyone in the world was doing at that time. And we were thinking, okay, how can we actually use that skill set? That's a pretty unique skill set that we have at the studio of industrial designers, of electronic engineers, of user researchers. How can we use that skill set to actually do something or support, even now, no matter how small? How can we help in this crisis? And so we set ourselves to do a short sprint, or like a design sprint, where we took as a first question is like, how can we use our skills to support in this shortage of PPE, personal protective equipment? So face masks, goggles, these kind of things. So that was an initial question. And then throughout this design sprint, we focused more and more on the shortage of face masks. And then we found out that there's actually quite some places in the world where people don't necessarily have access to face masks. And if they do, there's a shortage. And then we came up with this box where it's basically using existing components, a very, like most of the shelf is an IKEA box. Basically all components you can just buy at your local hardware store or easily sourceable online. And we made this box which is using UVC lights for people to decontaminate their own face mask. So you can basically take a face mask, decontaminate it, and use it again. So instead of using a face mask a couple of times, you can use it more often. And the great thing about this project is that we did this. We designed this whole kit, and as you can see, it's just basically an IKEA box with some other components, and we made it open source. So we shared our build plans. We actually got this box tested in Germany because, of course, we want to do something that actually also works, first of all. And then we put it online, and we saw it spread really nicely. So a lot of people made this in Central and South America, and people in Africa and Asia. So it spread really well. And it was just great to see how people with like very limited means still were able to build a box like this. And even though it was like a very short sprint, we got like quite a lot of traction from it. And then we even got to a point that we got approached by a Dutch agency to redevelop this box into a product for the Ugandan market. So now we're actually busy to take these principles of a UVC box for decontamination and translate this concept into something that can be produced locally in Uganda at very low cost and at scale for distribution in Uganda and later also different countries in Africa, where they can use it to decontaminate face masks, but also other things like phones, keys, like very, like basically everything people interact with. And this shows how like a small sprint eventually can lead to something more significant. Yeah.
So I'd like to drop in with a quick question for you both. There's lots of products, hardware products and embedded type products are often promoted on Kickstarter as projects, and if you follow some of those, they inevitably end up in lots of trouble and inability to deliver on time and things like that. What's your opinion on those sort of Kickstarter products? Is it just do they just need more support? Is Kickstarter even, should they be having those sort of those types of products on offer?
That's a good question. I think there's a twofold in there. First of all, I think if I as a professional go to Kickstarter, it's very easy for me to filter, or relatively easy to filter through these projects, and you can clearly see what people actually went through the efforts of properly testing, and like which are in a good point for Kickstarter. And you can also easily pick out the projects that are not much more beyond a concept stage, right? People make some fancy renders, which is very easy at this time, like with very little technical skills, you can already create something that looks like a product, but it's not much more than a concept, right? And my feeling is that Kickstarter could be better at filtering a bit between the products that they would allow on the platform. But at the same time, I think these crowdfunding platforms, and it's not just Kickstarter, it's also Indiegogo, and there's plenty of them, I think a lot of people who go there they consider them basically web shops with a longer lead time, right? The idea of a crowdfunding campaign to me is like you support a startup, or you support these people in realizing that idea. And then you also have to accept as a person that it's like you're funding it, right? It's not, you're not ordering a product, you're funding this idea. And with that, you have to accept that, okay, it might take like 3-4 times as long before I have this idea, I have this product. And when I get this product, it might not have all the features that they promised me or told me about in the beginning. But since people are so used to online shopping and all these crowdfunding campaigns, it almost looks like it's just a web shop with a long lead time. And I think that's one of the problems that people should maybe take into consideration when you order something on Kickstarter. It's like it's not really ordering, right? It's backing, and I think that's often leads to frustrations with the people who back something, because if you go often to the content, you see a lot of people complaining about things that I think like, okay, like you should have also considered this before you actually put money into it. But that's my opinion, of course.
I think Indiegogo is a platform that it does more filtering. I think there you need to present a business plan, and you have to show how serious you are and how far you are. And,
yeah, no, they like also these platforms they develop. Of course, it's not.
Jason, you wanted to say something?
I was going to say it seems those platforms are marketing driven, and it's the great marketers that are able to sell something that doesn't exist, and then the reality of the engineers and the industrial designers and everything that have to create that. There's that disconnect. It's basically the opposite problem that I have, I think. So I think we can learn a lot, but you could say the same for venture capitalists and things like that are putting a lot of money up front on an idea and great marketing about something. But at least there is a market. If you put something out on Kickstarter and get a huge response, then at least that you're in the right direction. There's been a lot of chat right now about marketing and how we advertise, and maybe that's just a great medium to do that. I think it's an option for us, but we have to, like Ruben said, there's a lot to be careful about on there.
One last thing I would like to say, I think a lot of people also that put projects on Kickstarter, I think they underestimate, and then Jason also touched upon it, the tremendous costs that are involved in creating a physical product. I think that's very much underestimated for a lot of these people. They don't understand that tooling for injection molding can easily cost 50,000 euros. So I think it's this might also be some lack of knowledge within the people that don't succeed on Kickstarter. And then indeed it's often like a marketing trick that they do, and they see the dollar signs and then don't realize that they actually have to deliver a physical product.
Yeah, some of them seem to be calculated very precisely, and you wonder how they're going to turn some of that product out. So I think we probably want to get to our competition, don't we, Clemens?
Yeah, well, to help, this webinar is in the context of the Elektor Helps series, and well, Jason expressed his difficulties with marketing, so I will help him a little bit with marketing. Buy this, please. Do it for Jason. Buy this bundle. Also, this book and this board. Please buy. It's not very expensive. You can buy it, and then it will help and will make Jason happy. And to get you buying, well, some people, we will give 3 of these away. This is the book. 3 copies of the book. We will give it away. We have to ask our lovely assistant behind the desk.
I think the names are there. So if Jason wants to read out who's won his Elektor bundle.
Sure. Let's start with the books, and then we'll do the grand prize if that's okay. So
Yeah.
for the 3 individual books, the names I see here: Ray Smith, Alvaro Aragada, and Everett Versteg. I apologize if I say those wrong. And our grand prize winner of the bundle, please send me the box when you're done with it, is Soon Johansson.
Okay, well then I think we can bring this webinar to an end. Here we have an overview of some links. So Electro Industry Magazine, you can download it from our website, of course. You can also find there's a typo in here. Memberships, you can find them on the memberships website. Jason's book and bundle are available from the Elektor store at elektor.com. The webinars, this one and also the previous webinars, are accessible through the link, the Elektor webinars page. And then we have videos. This webinar will also be on our Elektor TV YouTube channel, where you can find other videos about interesting electronics projects and companies and things like that as well. Okay, well, I would like to say thank you very much to our guests. Thank you, Jason. Thank you, Ruben. I wish you a lot of luck and success with Jason with marketing, and Ruben with finishing your guard wash device. Stuart, thank you very much for being with us and presenting your More Law article, and hope to see you soon with a new article about a new interesting subject. Maybe you can have you already have a preview for us, a sneak title preview?
For next month, we're going to look at mergers and acquisitions in the semiconductor industry.
Oh, would it have anything to do with ARM being bought by, who was it again?
Yeah.
Perhaps ARM being bought by NVIDIA may be part of the topic.
Okay, well, looking forward to it. With that, thank you to all. Thank you all the participants for being with us for this 1.5 hour. Like I said, if you want to look at it, re-watch it, it will be on YouTube on our Elektor TV channel tomorrow. Okay, thank you very much, and see you next time. Goodbye.
See you. Thanks very much. Bye.
Bye.